So in this video we're going to look at dot products of orthogonal vectors. So in the previous couple videos we've established this relationship describing the cosine of an angle between two vectors. So we found that the cosine of theta equals u dot v divided by the size of u times the size of v. And what we can do is use this to identify a property of orthogonal vectors. And orthogonal means, in the context of Euclidean geometry, it just means that two vectors meet at right angles, 90-degree angles. They're perpendicular to each other. It means something maybe a little bit different in the context of vector spaces, but for our purposes, orthogonal is going to mean two things meeting at right angles, or making 90-degree angle with each other. So a corollary to this theorem that we already established or derived is that if two vectors are orthogonal, their dot product has to be 0. And by corollary, what we mean is this just follows naturally from this result without really any effort. And the idea is, if two vectors are orthogonal, then we know that the angle at which they meet is a 90-degree angle. And so if we plug 90 degrees in here, so we do cosine of 90 degrees, and we know that that equals u dot v over the size of u times the size of v. Well, the cosine of 90 degrees is just 0. So you get 0 equaling the stuff over here. And the only way for this stuff to equal 0 is for the numerator to equal 0. So we get a natural result then is that u dot v will equal 0 if two angles are orthogonal. So this can be used in a variety of ways. It can be used to determine whether two vectors are orthogonal or not orthogonal. So if I want to find out if u and v are orthogonal, I can just take their dot product, which equals -6 plus 6, which equals 0. And I know, because the dot product is 0, that these two vectors meet at a 90-degree angle. They're orthogonal to each other. The other thing that it can be used for, actually, is to construct perpendicular vectors. So if I take any arbitrary vector I wish, and I want to make a vector that's orthogonal to it, I can just kind of randomly dump stuff in here. And as long as I leave this last spot blank, if I take the dot product, 1 times 2 is 2, plus 0 times 1 is 0, plus 6 times a, as long as I set that dot product equal to 0, and then solve for a, and dump that value in, so here's -1/3, now I have an orthogonal vector. And if I wanted a vector that had a nice component in the third spot, I could just scale this. I could say, look at that denominator of 3. I'm going to do 3 times the vector 2, 1, -1/3, which is going to give me the vector 6, 3, and -1. So now I have a nice vector with integer components that's perpendicular to the vector I started with. So using this fact that the dot product of orthogonal vectors is 0, it's going to turn out to be very useful. And when we in a little bit try to derive the equation of a plane in R3, we're going to use this idea. That's going to be what drives the result for the standard equation of a plane in 3 space.